Okay, I forgot to show you what happened when you start a Mathematica. Let's say I start a new notebook, right? It just comes blank, right? Notice that there's a plus here. There's a plus here. If you click on the plus, it gives you the option of what you want to do, right? Now, by default, see the word default here? By default, it's going to be this, language input, okay? So by default, if I just type in something like x is equal to 1, this is mathematics, right? But, okay, so that's the kernel, okay? I press enter, it goes x equal to 1, fine. If I want to start something else, I have options. Down here is the text. So if you want to write something that is not mathematical, you can say plain text. So I say x is equal to 1, and that's just a text. That's just hello, my name is blah, blah, blah. Okay. So this is just a text. Shift enter, nothing happens. It's just text. Also, there's other style of text. So you can say like a section. Now this is for publication. Now, the other thing that I was telling you earlier is here. These three things here. So let's say Mathematica has this as a main kernel. The Wolfram is this one. Okay, the Wolfram is this one. Now, this is like Mathematica entry, except it's free form. So you can write in English, and the Mathematica will try to interpret it. It's like Alexa kind of thing. So that's kind of like added feature. Finally, this is external language, meaning that you can use Mathematica kernel as a way to compute other things as well. By default, we set this to Python. So if I did this external language, it becomes a Python kernel. So I can actually seamlessly run Python kernel inside this. Okay. The other thing I was telling you earlier was about the Wolfram Mathematica. Like I said, we go to say we search for Thailand, right? Now, instead of just looking for the web page, it's just going to give you quantitatively computable information like total area. So all of this, you can double click and then create a graph and plot and stuff. So this is it's a much better starting point than wiki page if you want to do like a data-oriented research. Okay. There's some text as well, obviously, you know, some Wikipedia summary. So you get that as well written here. So you might as well not go to Wikipedia. In fact, I don't use Wikipedia if I can use this, because Wikipedia is just going to give you this, right? The text. Whereas here, you know, I can actually get plot on histogram of currency, people. So these are all kind of geometric data. I can do this. So all these are computable. I can do something more to this. So when I search over something, it's going to give you computable information that I can do something more. Yeah, obviously, you can do something more. Good. So like click to whatever. Okay. But anyway, we're not using we're not playing with Mathematica Alpha today, Wolfram Alpha today. So let's get back to where we were. Okay, so we did this variable assignment recall. We did this kind of table. Now, by the way, just now I was showing you that different argument like array 2, 3 is not the same thing as array bracket 2, 3, right? Because this gives you the dimension of the object, 2 rows, 3 columns. This one gives 2 objects starting from number 3. Now, if you are confused or you're not sure, you're not familiar, all you have to do is this. Click on the name of the object, the name of the function, and F1. And that's going to give you this. So this would be like looking through the manual of how to, so this is how to call the function example, blah, blah, blah. Generalization. Okay. So this is all the manual. Again, because it's a closed system, all the function in there has a very well written manual. And there's also related guide, workflow, tutorial. Okay. And this is something that this related guide and workflow is useful when we start to do data science project. So I want to do some kind of analysis, and I click the, oh, what can you do with it? You can do manipulation and so forth. Okay, but anyway, today we're talking about just bare bone. Today is just bare bone. So let's just do the bare bone, get the bare bone out of the way. So this is association and data set. We talked about that. Now, built-in function. How many of them are there? There are millions, well, not millions, 10,000 of them. Okay, but okay, let's see what's the usual suspect, right? If I did this exponential 12.34, what do you think is going to happen? Well, it's just going to give you exponential function, right? It's going to give you exponential function of this. So I can give you anything. So use this as a calculator. Okay. Now, notice there's a difference between this and this. You notice that? When I did this, exponential 3, there's an analytical expression for it. Okay, so that's e to the power 3. E is like 2.71 something. Okay, but if I put just a dot, it indicates that I want like numerical value, because 3 point is same thing as 3.0. So now it gives you numerical. Okay. So that's just a little shorthand for when in doubt, Mathematica will give you precise value. So if I give 1 divided by 3, it's going to give you this. It's not going to give you 0.33 because 0.33 is not as precise. Fine. Now, let's do this. So there's some function that applies to the list, like table form. This is a formatting function. This is only, so instead of listing it this way, it makes it look like a table that looks nice. Matrix form looks like this. So this is kind of formatting. Now, if I did this exponential 1, it's going to give you E, right? Now, I told you before, if I put in a dot, it's going to give you numerical. Another way of saying this is to say that I want numerical. I want numerical. And that numerical is n. So put n around it, get the same thing. Okay. Now, here's a shorthand. Because sometimes you can imagine if I did this 3 times, there will be 3 brackets. Okay. It looks a little bit clumsy. So the shorthand is to use what's called apply notation. So instead of doing this, I say 1, apply exponential to it. Oops, apply. Oops, apply. Right? Once I did this, I also apply this. Oops. Same thing. Yeah, same thing. So I can say, is this the same thing as n of exponential of 1? Yes, it's true. Yeah. So this is a function. This is a proper way of writing things, functional programming, right? You apply exponential function to 1, apply n function to the result. But you can also use this kind of shorthand. So apply exponential, then apply this. This is called pre-apply. There's another notation as well. It's called post-apply. 1, use it, exponential, and then send it to n. It's the same thing. This is, oops. You can put the bracket because, okay. So if I did this, this is called write apply. This is similar to what computer scientists call pipelining. Okay, so there are 3 equivalent ways. Okay, again, it's functional programming. You tell to your tools, I give you 1, take the exponential, get the result, take the result, evaluate numbers. I can say 1, pre-apply with exponential, pre-apply that with n. So it's n of exponential 1. Or I can say, here's a 1. Take it, apply exponential to it, get the n result of that, apply n to it. So this is kind of like same thing. Okay. So this is kind of a factory assembly line kind of way of thinking. Okay. Anyway, so that's, this is built-in function. Now notice you can use this easily because it's univariate. Most of the function you'll be using is multivariate. Not only that, it's polymorphic in the sense that sometimes you can put in 2 arguments, sometimes you can put in 3 arguments, right? Remember I told you that if you have a factory, I can supply the factory with steel, rubber, and aluminum because it expects those 3 things, but it doesn't expect milk, so you cannot send it milk. Well, imagine that most of the time the factory has steel as in inventory. So if you can assume that the factory has steel, I can just say, I'll just give you rubber and aluminum, right? Those are called default arguments, and it works the same way. Now, for example, well, I'll give you another function first. This one, logarithm, okay? Log 5, 125. What do you think that is? That function has 2 arguments. 5 is the base of the logarithm. So log base 5. Of what? Of 125. So log base 5 of 125 is how many times 5 has to multiply itself to get 125. What do you think that gets you? 3, right? Because 5 times 5 squared is 5, is 25. 5 cubed is 123. Now, this is what I mean by default. If I did this, I take away the 5, that's like applying, just giving the factory just aluminum and rubber, but not steel. What do you think is going to happen? Well, it gives you this. It gives you this because it's the most precise. So let me put that in here. How come it's not 3? How come it's not 3? Because the default base of a logarithmic operation is E, right? It's E. So if I didn't put this, if I put this, it's going to say log to the base 5, or I can say, log to the base 10 of, okay, this is also going to give you 3, right? But if I did this and give you a, right? Because this is the log to the base E, ln basically. Yeah. So this is what I mean by optional argument. The function itself takes 2 arguments, the base and the operand. But if you don't give it the base, the most normal base in scientific computation is E. Okay? And what's the value of E? By the way, and there's a shortcut for writing E. If you have this, try with me, escape, and this is special character. This is basically E, escape. Okay. These are something that, they have like a short, you don't have to memorize this, but I do because I use E all the time. I use infinity all the time. Okay, I use infinity all the time. That's another thing, by the way, Mathematica can actually compute with infinity. Okay, now this is another assignment, but this one is a string. So sentence called Jack and Jill went up the hill. And the function is called string count. Okay, and this is also multivariate function. Give me the string and give me what I'm to look for. Let's look for J, okay? So I can do it one at a time. Let's do this one at a time. Okay. This is equal to Jack, see? It turns black now. Now I'm gonna count how many J appears in here. 0. Why? Because I put in small j. But what if I put in capital J? 2, Jack, Jill. Okay. If I didn't put anything, this is like a joker. The underscore in Mathematica is a joker. Okay. So count anything. 31 characters. Now, what else? What else? What else is multivariate function? Well, you can think of logic, right? When you used to think about logic, you're not checking for something is true. You're checking true and untrue. So it's A equal to A, and it's 2 plus 3 is equal to 5. So that's 2, right? Check 2 things. Because this happens a lot, there's also a shorthand for it. And yeah. So this is a function. Now, and this is just me being funny. There's a function called apply. Apply this to that. Okay, when you say apply A comma B, you apply A as a function to B. So actually, function exponential 1, 2, 3, 4 is the same thing as applying the exponential to 4. The reason I write this here, yeah. So this is exponential 12.34. I get this. Yeah, I get exactly the same thing. Oops. Oops. Sorry. I did something wrong. Sorry. Apply. Let me come back to it. There's a notation I want to get to. Okay. If I want to apply this, I want to apply exponential function to A. I want to do it to B, C, D. Instead of making a for loop, remember, if this is procedural programming, I have to say for I equal to 1, 2, 3, and then a exponential I. In function, all you do is to say this and a list. Okay, so the first argument is actually a function. Now, this is very important for you to recognize right now. The reason I want to go to this example, very important, is a function doesn't just take value as an argument. It can take the name of a function as an argument as well. Okay, so the first argument is not a number, but it's actually another function. This function takes the first argument is a function, the second argument is a list. So this is what makes it functional programming, not just mathematical function. Okay, it is a function that expects here 2 things, this and that. This is what the action is. That is the list of things you want to perform action on. That's what this function map does. Sorry? Yeah, if I use apply, it's for some reason, yeah. So apply is this one. This is the apply. This is actually the shorthand for this. So I want you to think of this first. Okay. No, apply is different. Apply. Okay, let me go to here. Apply is one like this. It's taking this as an argument, so I don't know why it didn't work just now. It's oh, I know why. I forgot the bracket. Okay. Yeah. What? It's this is very subtle. Okay. The reason it looks like it's the same thing is because what I'm applying it to, right? But what's here? I'll show you why it's not the same. Okay. Let's do this. Why do you think this is not the same? This is good. This is very good. Thank you for that. Okay. What's the difference is this? A map. Say, give me an action. Okay, give me a list of things you want me to do it to. So this is a list of things I'm going to do it to. So I'm going to do this to A, do this to B, do this to C. Apply means give me an action and the content of that action. So if I give you this, it's not going to apply to A, then B, then C. It's actually going to apply to A, B, C. So if I did this, this is what I get. Doesn't make sense. I cannot apply exponential A, comma B, comma C. Right? So it's a little bit subtle. And the reason they have two of this, again, Mathematica has been around for 30 years. Takes feedback of what's useful. Okay, this here is useful when I want to repeat action. Yeah, this is useful to do action. This is equivalent to list comprehension in Python. But this here is more abstract. It's saying that I want to do something to a set of something. And so when I put this, it takes a whole chunk. Okay. I would argue that in data science, this one is more useful. And the shorthand for this, by the way, is add. So if I did this, exponential add A, B, C, etc. Right? But if I did this, okay. Slash add is a shorthand for apply. Oh, sorry, for map. So shorthand for this, exponential slash. Same thing. Yeah. Whereas this or this is all the same thing. Okay? Or escape, double E, escape, shift, Chinese hat, A. Now, I just happen to memorize this because I use this a lot. But basically, there's this thing called template. I'll show you later. I'll come back to it. Okay, it's very easy. There's a lot of shorthand that are built in because it speeds up for people who use it all the time. It's not really meant to be for class 1 or something. Okay, so that's that. Now, let me show you what else is interesting. So this here, this is a function that has no argument. Actually, it has argument, but it has default argument. This function, you take in statistics, right? Normal distribution. What is the most common normal distribution? Standard normal. Standard normal has 0, mean, and standard deviation of 1. That's what this is. So this is the same thing as 1 and 0. So if I didn't do this, same here. This function doesn't produce anything. It just registers that I'm talking about a normal distribution. What do I want to do from it? I want to generate random variables. How many? Well, I didn't specify, so it's just going to give me 1. But if I ask for 5, I'm going to get 5. Right? If I ask for random variate -2 and 3, what's going to happen? It's going to give you normal distribution with mean -2, standard deviation 3, so random variate. Okay. And now, notice, let's do this. See? Generate random variable, 5 of them, from normal distribution with mean -2 and 3. So I shift enter again. Look, the number is going to change, right? Because it's random number generated. Now, in operations research, I don't know if you know this, but there's this thing called control variant. What it means is that even though you're running random number, you want to repeat. Okay, that's called seeding the random variable. Now, if I did this, every time I enter, it's going to get the same number. So it's random number, but it's pseudo-random. It's not completely random. Okay, start from some number. Okay, so anyway, this is just a bare bone. I just want to show you what a bare bone is. Now, let's go to the next page. Now, this is where you start to work with yourself, right? Again, this is the website. Double click on this, and you go to the textbook. Defining your own function. So what's good about this is there's a huge tutorial. Now, for some reason, I like to take my omelet, put in a soup, make it omelet soup. So I define it as my function. Likewise, my function A here takes two arguments. Now notice the format. I have to put in my argument. I put in underscore here to say that it's anything that looks like this. It's the joker. Remember when you define a function, f of A, I want A to apply to anything that matches. It's called regular expression. Okay, there's a reason in computer science why regular expression is important to specify like that. But anyway, that's my definition. Give me A, give me B. This function is going to give A plus exponential B. Once I define this, now this is another equality. For function, it's not equal. It's dot equal. Okay. There's a technical reason why I'm not going to go into it right now. So if I define this, right now it's blue, right? Right now it's blue. Okay. Shift enter becomes black. So now I know what to do. So next time I use my function A, it's going to give you 12 plus exponential 34. Sorry? The dash means anything that matches that. So that's why the A here goes with that A. You stick anything in here, I'll call it A. You stick anything here, B. In a more advanced programming, you can specify that it only takes integer, it only takes real number. Okay, I'm not going to go into that. Okay? In fact, most of my work, I don't do that kind of specification. It's just going to turn error if it's not supposed to do that. Okay? So it's supposed to take factorial of 7.5. It can't do that. Now, that's a bad example because there's a gamma function. Okay, so yeah, this means anything, no further restriction. I'll call it A and I'll do this. Okay. Now, this is what I mean by user-defined function. Once you have this function becomes exactly the same thing as built-in function. You can use it anytime you like. Okay. Now, when you start the program, you have to iterate the definition because it's user-defined. Okay. Now, you asked me earlier about limiting the scope. And again, this is a little bit more advanced, but it's so useful. I'm going to introduce today one. Okay. So my coverage today is a blend of what I think is the most absolutely bare bone way of understanding programming and the most common. Okay. This is one of those things where I'm going to define a function. My function only takes one thing, V. Okay. This is an example. Now, this function, I'm going to have inside of this thing called module. Module is my way of localizing what happens inside. It's like what happens in Vegas, stay in Vegas, that kind of thing, right? What happens in here stays in here, unless I give it out. So in here, my module, followed by the first thing, is a set of things that is local. So anything I define in here, I can do whatever I like within that module, and nobody else will know about it. The module is the restriction. So I say n is equal to length of b, and I want b divided by n. So what does this function do? This function takes a vector, and each element of the vector divided by the length. So if I have a, b, c, it's going to be a divided by 3, b divided by 3, c divided by 3, right? That's it, right? Notice this n here is green. Green is like, yeah, it's known, but it's known locally. Nobody knows. In fact, if I type in n now, you can see that n in here is 3, right? Right? Within the program, n is 3. But outside the program, does anybody know what n is? No, nobody knows. Okay. So this construct, and again, I'm going to give you the notebook at the end of the class. These are the bare bone and the most useful. Okay. Now, and then after this, we'll start to do something that looks a little bit more interesting. This is another way of defining a function. Imagine that you want to make a souffle, right? You teach your maid how to make a souffle. So you write this recipe, give it to her, and she makes a souffle. What if you don't want her to memorize the recipe? You just want to show her how it's done and let her do it once. Okay? You define this function by doing it. So like monkey see, monkey do kind of thing. So this is what it means by a pure function. You define a function just like before, but you use it once. Now, it doesn't make much sense why, okay? But when you do a lot of professional programming, there's going to be times when if you start to name everything, you're going to have like hundreds of your own functions. And sometimes you don't, you just want to use it once. Well, it's like that. This is called a pure function. And the proper way of writing it is this, but the way it's actually used is this. Remember this, the function we did before? I define my function, take two things, take the first thing, add to the exponential of the second thing, right? If I don't want to name this, I just want to show you how it's done. I take the first thing, add to the exponential of the second thing, and then I apply to 12 and 14, 34. Okay, this ampersand notion is a shorthand for saying this is a pure function. So this, right? So notice that this is very different from earlier. It's saying that, look, I want to take the first guy, add to the second guy. What's my first guy? What's my second guy? This looks a little bit counterintuitive. Why would you want to do this? Why would you want to do this? It turns out that in data science, you do a lot of pre-processing. Imagine you get that, okay, let's do this way. Let's say I get a lot of data set, okay? And this data set comes in centimeter. This one comes in inches, right? I just want to divide whatever comes in inches, multiply by 2.54, okay? I want to do it once for the entire data set, okay? And the data set is really long. So I don't want to define a new function convert inches to centimeter. That's kind of silly. This kind of pre-processing happens all the time. So it turns out that this kind of silly looking thing, you know, defining a function, using it once and not using it again, it's used professionally. It's a very handy way of doing things. Okay. In Python, it's called lambda function. Okay. So this thing is actually shorthand for lambda. So this thing is saying, so I can do this, by the way. What's this? I can apply to a list of A, B, and C, D. Now you can imagine now I just have two, right? In a real database, I can have 1 million of them, and I want to do this operation. Okay, so that's that. Oops. Why am I not doing this right? Oh. Sometimes you see something like this and you can put sorry. Not quite sure. Yeah. Sometimes on the spot I get messed up as well. But it's a shorthand for doing things in a long, in a sequence of very long series of things. Okay. And once you do this, you can do it for many, for a really large data set, and it saves you a lot of time. Okay, now I've mentioned that, okay, so this is the bare bone, right? The bare bone. So this is my mind map. I show you that this is the bare bone, the variable, the built-in function, the user-defined function. Okay, so these are the core. Again, let me revise. What have you got? Okay, a variable, you have assignment, you have a list, you have a constructor, like table and array, you have association. So these are the two most fundamental, like dictionary and list. Okay, so association, list, database, these are the most basic object you play with. The built-in function, you need variant and multivariate, and the user-defined function, we have two versions, the one that you name, like my function A, and the other one that you use once. Okay, so that's kind of pure function. And this one you would use a lot in your application building. This one you would use a lot in your pre-processing. Like you have data that has to eliminate. Sometimes it gives you 1 billion and you just want 1 million. So you divide everything by 1,000 and that's it. You don't want to do it again. So that happens a lot. So this is the core language. This is core language. Now let's go to capability, functionality. Now this is where Mathematica becomes powerful. Okay. There are three aspects that makes it powerful. One is the big computation mode itself. What does it compute? And it can do analytical as well as numerical. In fact, all the language that you will ever know beside this, C, C++, Sharp, Java, MATLAB, Python, obviously, R. This is also going to do numerical. None of them is going to do analytical. None. Okay. And I'll show you a good example. Second functionality that's powerful is the visualization aspect. Okay. Again, you can do a lot of this with like Matplotlib, but it will take you half a page just to draw something. Okay. And finally, the other thing is there are two application domains that is very strong. One is machine learning and data analytics, which is why we're studying it here. And the other one is optimization and system control. Okay. Let's go over some analytical, and this is going to amaze. Now, I want you to copy this, but you don't have to copy this. I'll just give you to you. Actually, you go to the line. Oops, sorry. Okay, let me do this. Copy this, right? And go to the line group. Everybody see the line group, right? I'll do it later. Okay, so let's go to this example. So let's define this function. Okay, let's define this function. So I just define my function as x to the power 4. So this is analytical function. I can make it more complicated, but this is a little more intuitive. You know what this looks like, right? Because it's actually a fourth order polynomial. Okay, so this is my function. I just define it. Okay, let's look what it's that. And this is where, you know, it's a lot easier to do this. So all I do is plot 3D this function, and I give it the range of x over which I want to plot y, and I add this extra command just to add the link. That's it. Yeah. Now this would take matplotlib 11 lines at least. Okay. So now you got this 3D plot. Okay, this is a function. This is x and y, right? Once you got this object, you can rotate however you like. Okay. So that's it. Just one line gives you a plot. Now, here's an interesting thing. What if I want to take differentiation? Now, this function is simple, so you can do this in your head, right? What's the differentiate this with respect to x? So it's going to be 4x cubed, right? Nothing here, minus 10x plus 10y, nothing there, right? Well, there it is. Derivative with respect to x. Okay. Oops. Okay, I was writing no notation. Derivative of this with respect to x. There. Okay. Oh, I know what. I forgot to clear x. Okay. I keep using x again. See, the point is, this is a nicer way of writing what I wrote just now. See? This is analytical. Okay. Well, if this is integral, you can also integrate, right? Well, integrate this, okay, from, let's just say x from a to b. Okay. In a million years, you'll never get to do this in Python. Yeah. So actually, it's taking this equation, not treating it numerically, treating it as a mathematical equation, take differentiation with respect to x, get the result, integrate it with respect to get that. Okay? So this is the power. Now you can do double in differentiation. You can do that. You can do this, right? And now this is going to be very important. So I want you to pay attention to this. Just now, I have to define a function. Okay, I define this function. I plot it. Okay, right? So again, I define this function. This is my function. This is a built-in function called plot 3D. Plot this function over the range minus 4 to 4 plus 8 to 8. And this one, I just say, add some nice label to it. So this is the function. If I take derivative with respect to x, it's a partial derivative. If I take derivative with respect to y, it's partial derivative. If I want a direction that has the change, that has the greatest change, what do you think I'm going to do? I'm going to take the direction that has the maximum partial derivative with respect to x and maximum partial derivative with respect to y. And that is called gradient. So what's a gradient? Here, gradient. That's my gradient. as my gradient function. If this were an error function in a neural network, that's what neural network learning is. Let me say that again. Yeah, this is something that you guys, you know, if you don't get goosebumps, then you don't understand what I'm talking about. Okay, you understand what I'm talking about? It's amazing. Okay, so this is the function. This is what it looks like. If this were an error function of a neural network, say I'm training a robot to say hello, okay, and the robot say go away, you know, that's bad, right? So I teach it to do proper behavior. Well, the proper behavior corresponds to some kind of error function. And let's say this is my error function. And right now the robot is over here. And the best behavior robot should be over there. Mathematically, I'm asking the robot to walk downhill. Let me say that again, okay? If this were behavior, it's kind of scoring, okay? This is kind of like behavior error. And the least error you can have is say somewhere around here, this point here. To make that journey, instead of having the computer walk randomly, I tell the computer to take differentiation with respect to X and with respect to Y and walk in the direction that goes down the fastest. It's called steepest gradient. Okay, and that is essentially how I train my robot. I ask the robot to go down here. How the robot's going to go there? It's going to evaluate this first gradient. Now, as beautiful as it is in practice, it's probably done numerically anyway. So that's why the advantage that you can do this with Python, because Python can do numerical. Okay, Python cannot do this in the millimeter analytical. Okay, now what else cannot do? Watch this. I'm going to skip this. This is probabilistic. You guys know this? This is a very famous sequence. Okay? Mathematician in the Middle Ages came up with it. I'm not sure who. Okay. Anyway, one of the mathematicians. It's sum over I and j. J going from 1 to I going from 1 to infinity. Not to 10, not to 100, to infinity. Okay. This thing here is derived by a mathematician. But because Mathematica understands that it's a mathematical equation, it's not going to do this numerically. It's going to do this symbolically. And the result, anybody notice this convergence? Pi to the 4. Think about that. Think about that. It actually understands infinite summation. Understand infinite summation. It gives, so actually I can put in infinity here. Okay, the infinity is escape INF. Escape. Do that a lot. Okay. For example, if I this is a good one. Calculus. You guys know what the fundamental theorem of calculus is? Well, if you want to take the derivative of x to the 1, 2, 3, what do I do? Anybody? This, right? X plus delta to the 1, 2, 3 minus x to the 1, 2, 3 divide by delta and take the limit as delta goes to 0. Okay. That's it. This is not numerical. Even though you get something that's numerical, this is analytical. Okay. So that's why, but again, why would we do this? If you're a data scientist, a lot of times you don't do this. But there is one time, and I can show you this. This is from my professional work. I used to work as basically head of quants at a bank, doing data science. And one of the model of at the bank that I was working for was trying to do derivative, FX derivative. FX is like, when you buy dollar and baht, that's dollar, okay? Now, there's a derivative. This thing is called exotic derivative, meaning it's a very fancy way of doing funny things. So this is a Black-Scholes. This, by the way, is this in itself won 3 people Nobel Prize already, okay? But anyway, this is called vanilla. It's called vanilla. So I create something that's more complicated, okay? And here it is. This is what I need. And you don't have to understand all of this, okay? Basically, this is formula for pricing an exotic derivative. For financial professional, they need to know how to hedge this, how to manage the risk. And the way to manage the risk is to say that for every contract they sell, they have this amount of risk. And this amount of risk moves over time. To cover this amount of risk, I have to buy something else in some kind of ratio. That ratio is dynamically adjusted. So as the price of the dollar baht changes, this quantity changes every day, every second actually. To cover my risk, I have to buy something else. And let's say I want to cover my risk every 4 o'clock. Every 4 o'clock, I calculate this movement. And I say, okay, this is the amount of risk. This amount of risk has a ratio. And that ratio is given by derivative. So I have to communicate to a trader how much of something. I have a banana risk. In order to cover banana risk, I have to buy a fraction of apple. And that fraction of apple is given by derivative of banana to apple. I also have to buy a chicken. And the amount of chicken I have to buy is based on derivative of banana with respect to chicken. And I have to buy a fraction of a chicken. Okay, I have to do this every day. And this is why in Mathematica, all I do is evaluate differential. I take derivative of this with respect to S. S is my chicken. RD is my apple. T is my sugar. Okay. So this is actually a financial ratio that if I were to do this mathematically, it would take me maybe half a day and I probably get it. Okay. So this is actually done now. Well, but to be honest with you, from your perspective, and this is why you rarely ever use this, you can get away with numerical evaluation, everything. You can use numerical precision. Okay. But if you copy this, you'll be amazed that it can do this thing, this infinite series. Okay. So that's the analytical capability of Mathematica that nothing else in your life will ever do. Now, numerical it also does, but that's this is the same thing as what's inside Python. It's not that interesting, but I'll show you anyway. So for example, we had that function, right? We had that function, so we can solve, right? In order to find the bottom, what do? You take the gradient and you set it to 0. So basically, I solve the gradient equal to 0, and that gives you numerical. So basically, this is the location. Okay, look at this number. Minus 2.9 and 7.34 something. This is numerical. This is basically the location here. That's the bottom. So if you notice that it has a flat bottom, right? There are 2 points where it has a flat bottom here and there. That's what this number corresponds to. Okay. You can also use what's called fine roots. This is Newton's method. And this has been around since, well, yeah. You can also do optimization. For example, now this is where the difference between machine learning and optimization is. Sometimes in optimization, you can jump immediately to the solution. In machine learning, you go in incremental steps. But let's say you can do in one shot. That's what the solution would be. In this case, I actually can do one shot because I know where the zero is. Okay, it's very simple. But so this is numerical capability. Okay, this is nothing more special than gradient descent or whatever. Okay, so this is something that is plenty available. And to be honest, for numerical evaluation, you can get very fast library with Python. SciPy, NumPy, there's a lot of built-in tools that's very quickly. The speed is not the thing here. Now, visualization. So I'm going to cover this, and this is going to be the end of today. So this is what I mean by very simple. Now, this looks like a long, but I want to show you. This is very easy. Okay. So let's read from outside in. My data is equal to random variable. So I know I'm going to generate random variable. How many of them? 5,000 of them. What distribution am I going to follow? Well, I want to be a little bit fancy here. I'm going to give it mixture distribution. I don't know if you know what a mixture distribution is, but you learn about distribution, right? Like a normal distribution. Well, what if you have two of them and you toss a coin with certain probability? If it's head, you use this distribution. If it's tail, you use that distribution. That's called mixture distribution. So I'm going to make a coin toss with probability 1 over 11. Okay, probability 1 over 11. I'm going to generate binomial distribution. Now, binomial distribution is like normal distribution, but with two variables, which means 0, 0, standard deviation, and this is my correlation. Just focus on this. This is my correlation. Okay, so this thing here, actually, there's a 0, 0 here somewhere, but it's omitted because, again, shorthand. This thing is a normal distribution with standard deviation of 1 in X and Y and correlation 0.5. This thing is a binomial distribution with bigger standard deviation, to spread out a little bit more. And it's also centered at 2 and 2. And it has a negative correlation. So you can imagine this thing will give you 0 and 0, right? 1, 1, and positive. That's the thing, right? Now, this thing is going to be centered a little bit up here. 1, 2. Has a bigger standard deviation, that's twice the standard deviation, and correlation is minus 0.5. So it's going to give you something like that. So basically, I'm going to have this normal distribution. I'm going to toss a coin with probability 1 over 11. I will have this. With probability 10 over 11, I'm going to have the second. So obviously, the second one is going to happen. So I'm just making this up to look pretty, by the way. So let's see if that happens. Okay. So I generate this data. So let's do this first. Okay. So I get my data. Right. Now, I'm going to do this. I'm going to create some kind of estimate around it. So this thing is called smooth point density. Again, this is high level because people use this all the time. Kernel density estimation is done all the time. So there's a lot of default. So that's why it's defined as a high level description. That's my SPD. What does my SPD look like? Okay. What does my SPD look like? Well, what I can do is I can show my contour plot. Okay, I can show my contour plot. This is actually one line each. So imagine that this is my data, actually. I import my data. I create a smooth density. I can plot it right away. I can plot the contour plot of this kind of smooth surface over it, as well as the data point, the actual data point. That's my list line data point. Okay. Now, that's not very, so this is kind of like very quick way of doing. So right away, you see two things that are advantageous to this class. One line graph You can plot this thing in one line. You don't need 11 lines of matplotlib. Okay. Number two, it has a built-in kind of like model builder. So this is just one of so many different classes of model. This smooth density plot, smooth density is just one. Okay. So this is the capability I was talking about. So this thing gives you the plot and the graphic, but let's do something else. Basai students are not only interested in analyzing data, but they're interested in expressing their ideas as well, like maybe product display or something, right? So instead of just showing you a bunch of pictures, it would be better for you to display graphically, interactively, your idea. Now, for here, I'm just going to show you this same thing that I generated, okay? Except I'm going to do it interactively, okay? Now, notice it's the same thing as before. Watch this. Same thing as before, right? But instead of 1 and 10, I put this as a free parameter, right? Same here. The location of the second distribution is a free. I can make all this number free parameter, but this is going to get a little bit too much. I'm just going to make 1, 2, 3 things free parameter. And I'm going to do this. And I'm going to make a 3D plot. Well, I can make a contour plot first. But if you want to see a 3D plot instead, you just click this button. Become a 3D plot. Now, let's go back to contour plot because it's a little bit more obvious. Now, remember W, that controls how much of the leftward. So if I push this to the right, what's going to happen? What if I push it to the left? The first guy is going to be more prominent. Right? Now, this is how I would do my project. Okay? Except this one is tied to a mathematical function. This could be tied to, you design a pen. Okay? So you design a pen, you put in parameter that control the curvature of the pen. And then you put it here, and then you can move the curvature until you get a nice design. You can do that as well. Okay? So, and then once you have that, it becomes a computable object. What do? You generate 3D printing information, send it to a 3D printing shop. Okay? In fact, that's what we're going to have the Basai student do. This kind of exercise, creating rings and something like that, and then send it to the 3D. So this is already, and again, what else? I can move X around. Let's move X around. Okay, move Y around. So I can do this, and I can, plot this instead. So this become very interactive. Okay, this is interactive. In fact, in my own project, whenever I need to visualize something, this is my rule of thumb. To interface with the database of the client, my program will be written in Python. But to visualize what's happening to the model, I never use Python. Never could. But it's not going to take a long time. It's almost impossible in a project time. Whereas here, this is one line. Okay, this here, all it says is that, okay, I'm going to make an interactive plot. That's my manipulate. How many things do I manipulate? 1, 2, 3. What's the range of manipulation? From here to here, from here to here, from here to here. What's the initial value? Here, here, here. What am I going to plot? Well, I can plot PDF. I can plot CDF. Oh, I can do that. CDF. Let me get CDF. Right. CDF. My PDF. Okay. I can do contour plot. I can do 3D plot. Did that already. And delimiter, that just draws a line. It's just something to make it look nice. Write something, bold, medium, blue. The main action is here. Plot okay, X and Y over this, and this is the. So notice that this thing is not the name of the function. This name is actually a name of variable that allows me to select what function. So the choice of action to do is a variable. Okay, so this is something that, is very useful. So dynamic visualization, you can click to the page and take you there. So this is, I mean for this to be your thing to follow. Now, so I will give you this, and if you click through all of this, it's going to give you, so let's say one of you or two of you came from engineering school, and you're not so much interested in analyzing data. You're more interested in optimization, okay? Then you would go to something like optimization guide, okay? Optimization guide, and it does linear programming, non-linear programming. I actually use fuzzy optimization in finance. There's this thing called risk return optimization. You want a lot of return, you don't want a lot of risk. And that's using the quadratic function. But what if you want fancier version? You have different risk metrics, 5 of them. How are you going to put them together? Well, that's where fuzzy multi-criteria comes in. And I actually use that. Now, and I'm being a little bit cheeky here. Even though I write everything in Python, in Mathematica, there's a YouTube. So if you go, just search my name and go to playlist. Okay, PyCon Thailand. So if you go to here, I give a kind of keynote, I give a talk on Python. There's like a Pythonista annual meeting in Thailand before COVID, before COVID. So this is 2000 what something. Anyway, 2017 or whatever. Okay, this one, by the way, it's gonna be an ad on this. This one here, this second one here, is actually a presentation where I show you equivalent programming in Mathematica and Python. Okay, but obviously, Mathematica took me very short time to do it, and then I gave it to my staff to replicate it in Python so that I can even talk to Python. But anyway, so this is based on this optimization function. Hold on, let me go to. Yeah, this is, yeah. So this is basically, you don't have to listen to the whole talk. But basically, this surface here, remember I told you that we were trying to find the minimum? Well, in this case, we're trying to find the maximum. So the optimization algorithm actually programs all this in and trying to find the top of the hill. Okay, and the top of the hill then will become a solution to investment. So this is English, math, and Python. Okay, but I cheated because again, a lot of stuff that I generated was in Mathematica. But so this is the Python code for the optimization. And what it ends up doing is selecting allocation to different assets. Now, this problem here, technically speaking, is not part of data science. So for data analytics, the focus is different. The focus is to extract insight from data. This optimization is saying that you already got the model, you got the insight, but that insight leaves you with option to choose parameter. And you choose the parameter that maximize your benefit. Okay, so if you think of it this way, okay, there are three clouds of events. There's reality, the system. Okay, financial market, risk return, asset, financial market. That's reality. You measure reality, so you take the data, you take the data, take the time series, you record it, you put in Excel, you put in whatever, you pull it out in Python or Mathematica, and you do data analysis. Once you do the data analysis, you get the distribution, you get this thing, you know, just what we showed just now, right? And then if you have the ability to choose, for example, choice of allocation, then you go to optimization. So this echoes exactly what I said last week, was that you go from modeling, but you have this modeling reality of how it works. But you do optimization if once you find out how things work, you have freedom. Remember last week we talked about the example of the traffic, right? Modeling reality is when you say you go to, the reality is Bangkok traffic. Then you have somebody record Bangkok traffic. You take that, you build a model that simulates Bangkok traffic. Then, because you have the choice to play with the red and light green, let's say, or you can actually say magically turn this two-way road to a one-way street, or pedestrianize this, or make this a 3-lane to 2 as opposed to 2 and 2, whatever. Okay, those are your optimization parameters. The optimization is to choose this thing to do something. Minimize traffic flow, maximize flow. Maximize flow, minimize traffic congestion. Maximize flow. Okay, maximize flow, minimize congestion. Same thing here. I want to maximize risk. I want to maximize return, minimize risk. And there are many risk criteria. So this would be the Python talk. A year before that, I was talking about graph theoretic. This is also a very interesting thing. If you're into Python, I use what's called Network X. Again, I had my staff do most of the programming because I really am not a good Python programmer. Okay. So the concept is here. Okay, and if you go to, so these are the two powerful things that Mathematica does well. Machine learning, data analytics, again, because it has a large class of built-in machine, and it does optimization. Okay, so just you can do analytical optimization in certain cases, you take derivative, and you can do numerical as well. So, for example, just now that we saw this thing, this numerical, NSOLVE, there's also an analytical version called solve. Okay, so it depends on how you want to approach it. Some problem gets so complicated, you cannot do analytical anyway. Okay, you know that, right? Like Fermat's last theorem, things like there are things where mathematics is not doable in closed form. For example, you can say quadratic formula, you can find it, right? X squared plus, you can find an exact formula. You don't have to equate it. Once you go to the 5th order, you can't find analytical solution. You have to go numerical anyway. Okay, in that case, you might as well go to Python because they have fast algorithms to do things. So, yeah, you have solve function for analytical and NSOLVE for numerical solve. So that's that. Now, here's the homework. Here's the homework. I haven't decided yet how we're going to do the agile. It may be groups, but what I want to do is individually first. Think of individual term project. What data set you want to do? Now, here's where I want you to go to here. Okay, this environment. Go to this here. Data repository. Now, this, I'm going to go to the website. Okay. This is a little bit like going to Kaggle, except this is curated. Okay, Kaggle is as well curated as the provider. So if I'm very good curator, I give it to Kaggle, it's very good. If I'm a lousy curator, I give it to Kaggle, it's a lousily curated. So this is the data set. And there are many categories: physical science, geology, education, economics. So let's say you're interested in health, you go to health data, Spanish flu, epidemics, list of epidemics by country, and you can go to, if you're interested in, I don't know, maybe life science, yes, life science, good. Go to so what I want you to do is browse through this, and they come up with a list, not a list, the data set. Maybe if you haven't made up your mind, you can come up with one or two. Okay, but your TA is going to create like a my course view. So you go in there and you say, I want to work on this data set. Okay, so for example, I want to work on hospital resource water supply monitoring. Now, what's good about this is that it's not just like cake where you give the data, and it actually has some analytics already built in. So you do like time series analysis and list date plot. These are all built-in function. Okay, so you can download the data set. You can also download the program to play with it. So what I want you to do is shopping for data set to play. Okay, so think of this as I'm not going to hold you completely accountable. You cannot change. You can change. Okay, but I want you to make a commitment as if this were to be your third project. Okay, again, at the end of this class, you will have experience taking the data, see what you can do with it, do something with it, draw some insight from it, make some conclusion from it, as if you were a professional data scientist. But I'm not going to require you to work on the same data set or my data. You can play with whatever data set you like. And the first thing is go through this repository here. I'll send you both the mind map and the thing here. Okay, and let's make it by maybe Friday morning, maybe. Yeah, good. Yeah. I say by Friday morning, you have to commit yourself to one data set. Okay, and this is a data. So don't just go for easy, by the way. Go for something you really want to do. You want to know about astronomy, go to astronomy set. Okay. Now, I don't guarantee that I'm going to be able to help you throughout this, but we can do this. What's going to happen next week is that we're going to play with maybe I'll just pick 5 of you to come discuss. Okay? It's random. Okay? And then you say, okay, this is the data, and then we start working through what a professional data scientist would do. Well, the first thing, by the way, is check for NaN. Check for empty. Okay. But anyway, beyond that, you're gonna start thinking of, can I fit normal distribution to it? Can I check for this? Can I check for that? Is there a correlation? That sort of thing. So this kind of, what do you think we can do with it? It's the first step we do as a data scientist. Okay. Again, you have complete freedom, so choose wisely. It's huge. The database is huge. Okay. And the visualization, it's amazing. So you can play with that. Scatter plot, distribution of plot. Use what I showed earlier. Create a smooth function over the data set. Okay. Today I show you a lot of analytical capability that I don't think, for your purpose, I don't think you should focus very much on. Let's focus on numerical probabilistic statistics. Okay, like that function I show you, it's not analytical. This smooth kernel, it's called kernel of non-parametric statistic. It's very numerically oriented. It's like saying every point, it's like this. Instead of saying this is a certain distribution, I say, give me all the data set. Okay, give me all the data set. And every single data set hold up an umbrella. Okay, or hold up a mushroom. Every data point holds up a mushroom. And I add the height of all the mushroom. It's going to smooth out. That's called kernel estimation or kernel fit. Okay. Except instead of using a mushroom, I use a Gaussian function. It's the same thing. Okay. Play with that. Friday morning. Yeah, Friday morning. Those of you who have problem with download, again, download the player first. I'm going to save the file here as .cdm. Okay, everybody gets .nb notebook. Okay, I'm going to save it as a version called .cdm, computable document format. You can use that program to open it, and you can click. You just can't write or save. Okay, Yeah, that's it. So today, again, try to be on time. Hopefully, we'll start on time next time. We get this thing sorted out with the speakers and whatnot. Come on. My course view. Okay. Yeah. อะไรครับครับผมยินดีลูกยินดีลูกถ้าอยากเล่นนี่นะโปรแกรมเนี่ยคือโปรแกรมเนี่ยถ้าไม่ register ไม่ได้ก็ต้องขอมาได้เพราะว่าเรามีประมาณ100 license เพราะฉะนั้นเด็กที่เรียนเทอมที่แล้วเนี่ยตอนนี้ก็เป็นหลงก็ได้ใช้กันแล้วก็เวรคืนแล้วก็ไปใช้ได้แต่ต้องติดต่อคุณติดต่อ TA แล้วเดี๋ยวเขาติดต่อ TA คือพี่ก๊อฟคนนั้นนะคนนั้นคนที่นั่งอยู่โอเคครับ Yeah, but I try to focus more on project, but the exam is good. It forces you to sort of like consolidate.
Yeah.
Things.
And you know the date?
It would, I don't know. It's kind of midway. I think it's check the schedule. It's the same date. There's 1 week where every class has a midterm.
Yeah, but
it's that Tuesday.
It's that Tuesday.
Yeah, it's Tuesday at the same week as everybody else.
And at the same hour of the class, that's one. And the same class.
Yeah, you just come in here and you just come in here. There'll be like an exam program, but you just sit here.
Okay.
ครับคลาสนี้อยู่ใน YouTube yes แต่ครั้งที่แล้วเสียงมันไม่รู้นะเดี๋ยวเนี่ยYouTube ใช่ไหม Yeah this one นี่ไง DataAnalytics แต่เสียงไม่ดีเลยไม่ออกใช่ไหมอ๋อมันไม่ออกไหมเนี่ยไปเสิร์ชชื่อผมแล้วมันจะมีใน playlist มันจะอยู่ในหลายๆวิชานี้จะชื่อว่า DataAnalytics Autumn 2022 This oneใครติดไม่ใช่หนูนะ
ไม่ใช่ว่าตกวันศุกร์คนที่ติดโควิดวันนี้จะดูติดวันหรือว่าเรา
ไม่ยากนี่มาใส่ไปเลยยูก็ส่งลิงก์เนี่ยแล้วคนที่ติดโควิดเขาดูซูม
ก็เดี๋ยวต้องรีบตัดคลิปแล้วก็โพส
แต่ที่ถ้าติดซูมเนี่ยให้ขอแล้วลิงก์เอาได้
แล้วที่อย่างนี้เพื่อนเขาก็น่าจะแชร์กันหมดก็เลยตอนแรกก็เลยแชร์บอกให้เขารอดู
โอเคก็ได้โอเคก็พี่ไม่รู้จะรอดหรือเปล่านะคลิปนี้หมายความว่าเรา จริงๆต้องส่งเหมือนกัน
ตามนี้เลยเหรอครับ
จันทร์เนี่ยจันทร์หน้าเนี่ย
โอ้โหจริงครับ
เพราะฉะนั้นพรุ่งนี้ก็ไม่รู้สิไม่ค่อยไม่ถึงกับ
พรุ่งนี้ไปครับ
เออ